it's the same thing, so we're going to have to graph it, but it's 3 plus I over 1 plus I. And I know that you have to multiply it all by 1 minus I to get the...
Yeah. In other words, this looks like a division problem, but it really is not. Any more than if we talk about radicals. If you see this 1 over root 2, that looks like a division problem, but it really isn't. All it is we have to rationalize the denominator. So we multiply top and bottom by root 2, and we end up with root 2 over 2. Well, you do a similar thing with complex numbers. You don't really perform any kind of a long division. What you do is you make the bottom real. What I call it is realifying the denominator. And the way you make a complex number real is by multiplying it by its conjugate.
Yep.
Okay? Since I'm multiplying the bottom by that, I have to multiply the top by that. Let's do the bottom first. This is where it's really good to be familiar with difference of perfect squares. In other words, if you recognize difference of perfect squares, then you probably recognize difference of perfect squares factored. So, and this is difference of perfect squares factored. So to put them back together again, you know you're going to end up with the difference of squares, right? You're going to end up with 1 minus I squared.
Yeah.
That's just a little trick to make it a little faster when you are multiplying a binomial by its conjugate. So it's going to be 1 minus I squared in the bottom. What does that turn into? What's I squared equal to?
-1, so it'll turn into 2.
Okay. So we've realified the bottom. Now we're going to have an imaginary number in the top, but that's okay. It's a little like rational numbers. You can stand one in the numerator, you just can't stand it in the denominator. So on the top, let's figure out what we have here. What do we have?
3.
Go ahead.
Plus 1I minus 3I, which would be -2I. Minus I squared.
Simplify that.
Hang on. Let me write that down.
Do you have a chance to look at the recording of yesterday's session?
No, not yet.
Okay. I'm curious to see what you think, whether you find it useful or not. But it also, not that I'm suggesting you don't write it down, but you always can go back and reference this stuff. Writing it down probably actually does serve a useful purpose in, locking it into your brain. I think that's an excellent technique to learn stuff.
Okay, so then it'll turn into
what complex
4 minus 2I over 2, which will turn into 2 minus I.
There's your answer.
Yep.
It's funny, the answer sometimes doesn't look, in other words, what we're saying is that thing right there is the equivalent of that.
It's weird.
It is weird. Complex numbers are weird.
Mm-hmm.
Okay.
Okay.
And that's the hardest thing to do with complex numbers. Like I said, adding them, subtracting them, and multiplying them are very easy. If I was like we just multiplied the top, just FOIL it like you would any binomial. In other words, the fact that it's a complex number doesn't really matter.
Okay.
You just want to convert. You want to convert all your I squareds to -1. That's really kind of the secret.
Okay. So for this next one, it's just telling us to factor and solve.
Okay.
So it's 6x squared plus 23x plus 21.
Now, did they say factor and solve? I mean, does that...
Yeah, it says factor and
Okay,
solve.
so it's probably factorable. Because there's kind of a fine line here. When I see a quadratic like this, I know that it might be factorable, and I can spend 10 minutes trying to find the factors. But if I don't find them in 10 minutes, then I give up and I go to the quadratic formula. Right? That's the process. And the question is, what's the proper length of time before you go straight to the quadratic formula? In other words, if it's complicated enough, and I think that there's probably not much chance that it's going to be factorable, I'll go straight to the quadratic and save myself time. But since they said factor it, let's try to factor it. Can't take a common factor out, so we're stuck trying to factor that. What should I try in the slot on the left, where it's usually x and x?
6x.
Have you done this already?
No.
Okay. I'm going to suggest that whenever you're factoring and you're doing any kind of a trial and error, always use the two factors that are closest together, which is 3 and 2. You may end up being right. It might be 6. I don't know. But let's try 3 and 2. What are the signs? Both of them.
Plus.
In other words, the next thing to determine is both signs. What are they? Plus, plus.
Yep.
And now factors of 21. That's it. And 7 and 3. Clearly 21 and 1 is not going to work, right?
It's 7 and 3.
Yeah, it is. Again, always start there. If that doesn't work, you can try 21 and 1. Just like if 3x and 2x hadn't worked, we'd have then gone back, tried 6x and x. It really is a trial and error process, no matter what method you use. But yeah, you're right. The 7 goes there and the 3 goes there. Now, let's just talk about factoring for one more minute. When I have factored something, I never need to check to make sure that term is correct. I never need to check to make sure that term is correct. Just the way I factor, those are always going to be correct. The term that I need to check is the middle term. And the way I check the middle term, or the way you get the middle term, is by multiplying the insides together and the outsides together. And that's all the check you need to do. And then add those together, you get plus 23x. That indeed is the middle term. We did it correctly. So let me just verify that you're up to par here. What's the solution if I say set those equal to 0?
X equals -7/3.
Okay.
And x equals -3/2.
Okay. Cool. Is that all they wanted you to do, was to factor that?
Yeah.
Okay.
Okay, next question.
Uh-huh.
So, solve.
Okay.
Parentheses 2x plus 1 and parentheses, start parentheses, x plus 2 and parentheses equals parentheses 2x plus 1 and parentheses x minus 3.
How are we going to solve this?
We have to factor it out on both sides. Not factor it out, multiply it out on both sides.
Normally, yes. And then you would gather all your x terms on one side and all your numbers on the other. But notice we can take a shortcut here that'll make this whole problem much easier. Bless you.
Thank you.
What is the shortcut?
Subtract the 2x plus 1.
Divide by it, not subtract.
Divide? Okay.
Well, because right now it's a multiplier. In other words, that is multiplying that. So subtracting it wouldn't get rid of it. It's only going to get rid of it if this quantity was being added to one side of the equation. If it's a multiplier, then we have to divide both sides by 2x plus 1, and that gets rid of it. That cancels with that, becomes 1, leaves me with that. This cancels with that one. And notice now how much easier the problem has become. And now we don't even need the parentheses. What's the next step?
Then you
Go ahead.
subtract the x.
Okay, so what are you left with? Well, no. In other words, the next step in trying to solve this is to move all the x's on one side and all the numbers on the other. So I have to subtract x from both sides, which leaves 0x equals negative 5. Well, it basically leaves 0. In other words, what it really leaves is the following. X's fall out, and you get 2 equals minus 3. What does that tell you?
It's not possible.
There's no solution. There's no solution.
But we hadn't learned that yet, so what if we did it the way that I had started in the beginning?
Well, you're still going to get the same problem. Let's do it real quick. Well, you have actually learned it. In other words, you've learned that you can divide both sides of an equation by the same thing. Anything. Doesn't matter what it is. As long as you do it to both sides of the equation, it is equal to 1. Okay? So let's multiply these out, and I'll show you that it's the same thing. 2x squared, let's see, plus 5x plus 2 equals 2x squared minus 5x minus 3. Okay, now the 2x squared, excuse me?
I don't, oh, okay, keep going.
Subtract 2x squared from both sides, gets rid of that one, gets rid of that one. Let's see, if I move the 5x over to here, I have 10x equals minus 5, and now x equals minus 1/2. Now I get it. I violated a very special rule that you can't violate. In other words, there's one caveat to dividing both sides of an equation by a variable. And that is, if that variable is equal to 0, you lose that solution. And that's the mistake I made. This is actually a very good problem. I didn't realize it. But notice that when I divided both sides by 2x plus 1, well, I do have a solution of x equals minus 1/2, because when x equals minus 1/2, this is equal to 0 and that's equal to 0. And now 0 times x plus 2 is equal to 0 times x minus 3. So there was a solution to this problem that I didn't find the first time because I violated that law. And you got to be very careful about dividing by variables that might be 0. Because if that is a solution, you lose it. It completely disappears. As you saw, the first time we did the problem, I got 2 equals minus 3, so it made it look like there was no solution. Yeah, this is an interesting problem. Yeah. Yeah, you got it's kind of. Let's talk about another one similar to that. If I said this, hold on, I don't mean that. I mean this. And notice that what would your first step here be?
Divide by 6x.
Okay, what do I get? I get x equal 1, right?
Yeah.
I lost a solution. Clearly, 0 is also a solution, right? If you go back up and you look, x equals 0 works. And if it works, it's a solution. But I lost it because I divided by a variable, x, which might be 0. And if it happens to be 0, in other words, you will lose that solution. So there's a better way to do this problem such that we don't lose the solution. I don't ever want to divide by a variable if it could possibly be 0. So what I do is I subtract 6x from both sides, like that. And now when I factor out the 6x, I'm left with x minus 1 equals 0. And now notice, now either that can be 0, which means x is 0, or that can be 0, which means x equals 1. So if I do the thing properly, I get both solutions. And this is kind of the classic illustration of why it's dangerous to divide by a variable that potentially might be 0. You know, the first rule in mathematics is you cannot divide by 0. And what we're essentially doing is violating that rule when we divided by 6x. And I did the same thing up here without realizing it inadvertently. In other words, I divided both sides by 2x plus 1. Well, it turns out that 2x plus 1 is equal to 0 is the only solution. So I lost it. And the only way to really do this problem properly is the way we did it the second time. It's an interesting problem, very interesting problem. But that's something that it's worth remembering about dividing by things that might be 0. Notice you don't ever have to worry about multiplying by that. In other words, you can multiply by a variable, and if it's 0, you won't lose it, because it's okay to multiply by 0. It's just not okay to divide by 0. All right, what do you got next?
So that's a word problem.
You should have realized when you gave me that problem that there was something beyond what was normal, because you're in an honors class. And I couldn't quite figure out why they're giving you this problem. Now I understand. Go ahead. I'm sorry. What was the next one?
Last summer while golfing at Thorn Creek Golf Course, I noticed that one of the fairways created a linear line. Y equals 0.0007x plus 0.085. If the height of the golf ball can be modeled by the quadratic function, y equals negative 0.0009, parentheses, x minus 148.9, and parentheses squared, plus 19.99.
And this does what? This models the path of the golf ball?
The height of the golf ball can be modeled by the quadratic function. Then I was wondering.
Oh, go ahead.
Then I was wondering how far away the tee from my ball Then I was wondering how far away from the tee did my ball first hit the ground on the fairway. Let x equal horizontal distance and y equal vertical distance of the golf ball. Show algebraically and graphically.
All right. This second quadratic, you said it models something of the golf ball. The head of the golf ball?
The height of the
Height
golf
of
ball.
the golf ball. Okay. So here's our graph. That's the linear distance. The golf ball is going to go in a parabola, and it's going to come down right there. And that parabola is defined by this second equation. With me?
Mm-hmm.
So I can figure out when it's going to hit its height, when it's going to come down, where it's going to come down. What I'm confused by is that first equation.
Last summer while golfing at Thorn Creek Golf Course, I noticed that one of the fairways created a linear line. And that's the equation of the linear line.
One of the fairways created a line. Okay. It was straight. That's all that means. No. He's saying the height of the fairway. Okay. I got it now. So there's the fairway. That's supposed to be a straight line. Okay?
Okay.
And furthermore, it doesn't go through the origin. It's going to go, nor does this parabola go through the origin. Let's see, this parabola. Anyway, let's plot our linear line. Okay, and we need to figure out what that point is right there.
Okay.
That's where it comes down. That's where it hits the ground. Because the fairway is uphill. That's what they kind of meant by a linear line. It forms a slope. And the definition of that slope would be this line up here.
Okay.
Okay? So the question is where it comes down or when?
The question, how far away from the tee?
So we need we need this distance right here.
Okay.
Okay? All right. Well, that distance is the x-coordinate of that intersection point. So how do we figure out that intersection point?
I don't know.
By setting the two y's equal to one another.
Okay.
Because in the first equation, that's the y-coordinate. In the second equation, that's the y-coordinate. So they are equal to one another at that point. The x-coordinates are equal to one another also. But let's solve for the x value, and that'll give us the distance. So all I'm going to do is set this equation equal to this equation. This is a picture. Let me erase it so I can do some math. So I got 0.007x plus 0.085 equals that. Well, let's see. What's the best way to do this? I'm trying to think if there's an easy way to do it. There's a hard way to do it, which we don't really have time to do, which is to multiply that out, distribute that, and solve the equation. Okay? In other words, it's certainly an equation in one variable. Just the question of how, if there's an easier way to solve it. There might be an easier way to solve it. Yeah, there is an easier way to solve it. For starters, I'm going to subtract 19.99 from both sides. which on the left is going to give me this. Oh, what is that? Minus 19.005. Yeah. And then on the right, I'm left with that. So now on the right, I'm going to divide both sides by minus 0.009. And that's going to get rid of that coefficient in front of the parentheses. Notice that this number is not being squared. Okay? So I can do that. And so now I have this whole thing equals this whole thing. It's very problematic. You can't really take the square root of both sides now because I still have x's over here. I'm just going to make it more complicated.
Well, then maybe we should undo that and factor it out on the other side.
Yeah, the only solution I see to this problem is solving it the hard way. In other words, do exactly what I suggested. It's just complicated algebra, but you should be able to do it. You may end up having to resort to the quadratic formula. I don't know why they want to torture you so much using these oddball numbers, but they decided to. So take that, set it equal to that. Okay?
Okay.
Expand that, distribute that, put it all into a single quadratic and solve it. And when I say put it all into a single quadratic, put it into this form. In other words, after you've done the squaring of that and the distributing of that, now put it all on one side, and you'll be left with some number of x squared, some number of x, and some number.
Okay.
And now to solve that, almost certainly is going to require the quadratic formula just by looking at these numbers. Like I said, I'm not sure why they want to torture you with all of this arithmetic. That's why I thought there might be an easier way to do it, but I sure can't find it. But anyway, you'll solve for x, okay? And x, you're going to get two solutions because it's a quadratic, but remember what solution you're getting. In other words, the golf ball is like that, the fairway is like that. Well, that's one solution for x, but that's another. You want the furthest one away. That might even be negative. Probably will be.
Okay.
Just where the line would intersect the parabola of the golf ball on the big starting end. Okay? But
Okay.
so make sure you take your largest value of x, and that's how far the golf ball travels down the fairway. In other words, this is not the fairway, but it actually brings up another interesting point. Are they asking for this measurement down here, or are they asking for the length of this line from there to there? Because if that line represents the fairway, you're on a sloped fairway, your golf ball is going to hit up here. Well, that's not going to be the same x value as down here would be if your golf ball traveled all the way down to a flat fairway. It will be different. But it's the x value you're going to get doing the problem the way I suggested. In other words, that when you set the parabola equal to the straight line, you don't get this x value down here on the x-axis. You get the x value at that point right there. Okay, so that gives you some x comma y, and that x is that distance right there. And that is how far you are from the tee.
Okay.
Okay? That's a crazy problem. I don't know.
Okay.
I don't like giving students problems like that because it turns it into a giant arithmetic problem. It kind of ignores the concept that you're trying to get across, which is a real life concept. I mean, you know, you could go to the golf course and actually do this, figure out how far your ball is going to go. But all these numbers they put just make the problem so hard arithmetically, especially if you end up having to use the quadratic formula. Okay, for next week, do you want to go back to Monday and Wednesday?
Yeah.
Let me make sure. I think that's the schedule I have you on. Yeah, I got you Monday at 4:30 and Wednesday at 4:30. And I will leave those locked up for you until you tell me otherwise.
Okay.
Okay, Julie. Have a good week. Talk to you next week.
Okay, thank you. Bye.